Good morning and welcome back to my channel. Today we are going to discuss on a radiation physics topic, X-ray production and properties. X-ray production and properties. Let us see the discovery of X-rays. X-rays were discovered by a German physicist named William Röntgen in the year November 8, 1895. While he was studying the cathode rays stream of electrons in a glass discharge tube, he observed that another type of radiation was produced perceptibly by the interaction of electrons with the glass walls of the tube that could be detected outside the tube. This radiation could penetrate opaque substances, produce fluorescence, blacken a photographic plate and ionize a gas. So when he was studying a cathode rays in a glass discharge tube, he suddenly observed that another type of radiation was also produced, which was detected outside the tube, and the peculiarity of this radiation was it can penetrate opaque substances, produce fluorescence, blacken a photographic plate, as well as it have a potential to ionize a gas. He named his discovery X-rays because X stands for an unknown factor. So which all are the properties of X-rays? It is usually asked for many exams and we have to know a general ideas of X-ray. X-rays are invisible. As we all know, radiation can't be seen. X-rays have no mass. X-rays travel at the speed of light in a vacuum. X-rays travel in straight line. They have a very short wavelength. They are unaffected by electric and magnetic field. They cannot be refracted. They cause ionization, adding or removing electrons in atoms and molecules. They are transmitted by pass through healthy body tissues. They affect photographic film in the same way as visible light, turning it black. They are absorbed or stopped by metal and bone. They cause photoelectric emission. They are produced. So X-rays are produced when a beam of high energy electrons strikes a target. So a high energy electron strikes a target. It results in the production of X-rays, and these properties makes X-rays very useful for medical diagnosis as well as treatment. So X-rays are used in the radiology department as well as in the radiation oncology department, which I was discussed in the previous slides or the previous topics. X-rays are used as a mode of beam in the X-ray unit for taking X-rays. Likewise, the X-ray beam is used in the CT scan for taking images of cross-section of the human body. Likewise, X-rays are used in the radiation oncology, as in the case of radiation therapy treatment, as radiation is used for the purpose of therapeutic or treatment purpose for treating cancer patient. Again, let us see the X-ray tube. X-rays are produced in the X-ray tube, which is located in the X-ray tube head. X-rays are generated when the electrons from the filament cross the tube and interact with the target. The main two components of the X-ray tube are the cathode and anode. So, which is the component of the X-ray tube? The component of the X-ray tube is a cathode as well as the anode. The cathode is the filament and anode is the target. Cathode. Let us see step by step cathode. Cathode is composed of tungsten filament. So which is the material formed of cathode means tungsten is the material. The answer for that question is tungsten is the cathode material and it is seen in the form of a filament which is centered in a focusing cup. So in the area of the cathode there is a focusing cup too, and the cathode is formed of a filament and the material used is tungsten. The electrons are produced by the filament. So the filament is producing the electron. As we have discussed in the properties of the X-rays, when a fast moving electrons hit the target, X-rays are produced. In the before slide, I told you that cathode and the anode is a component of an X-ray tube and the cathode is the filament. So the electrons are produced from the filament. Electrons are produced from the filament which is focused to the anode. So anode is the target, and that when these electrons hit the anode target, the X-rays are produced. The focusing cup has a negative charge like the electron. As you all know that electron is a negative charge. So the focusing cup has a negative charge and this helps direct the electrons to the target, and you can see a cross-section view of the focusing cup as well as the filament tungsten. It will be seen like a circular filament. Next is the anode. Anode in the X-ray tube is composed of tungsten target embedded in a copper stem. So the material used as anode is also tungsten like that of cathode, and why we have chosen tungsten will be discussed in the upcoming slide. And this tungsten target is embedded in a copper stem. Why we are using copper? Okay. So when this electrons is coming and hitting this target, out of 100%, if we are taking 100%, only 1% of X-rays is formed and 99% is formed of heat. So in order to avoid this heat or take away this heat, we are embedding this tungsten in a copper stem. So why we are using copper stem means, in order to take away this heat from the target, we are embedding it in a copper stem, since the target should not get too much of hot, since if it receives too much of hot, there is a chance for cracking the target. Why tungsten is used as a target as well as the filament? The choice of the tungsten as a target material in X-ray tube is based on two criteria. It should have a high atomic number as well as a high melting point. So the atomic number of tungsten is 74 and it is good efficiency or good in X-ray production. The efficiency is depending on atomic number. So the tungsten is used as the target material and it is having a high melting point of 3370 degrees Celsius. So it can withstand too much of heat when the electron is bombarding. So these two are the main peculiarity for choosing tungsten as the target material, and tungsten can be recoiled as a filament. So tungsten is used as a choice for cathode. So what is meant by thermionic emission? When a high voltage is applied between the cathode as well as the anode, the electrons are emitted from the filament, which is accelerated towards the anode and achieve high velocity before striking the target. So the filament is getting heated up to producing the electrons when a high voltage is applied between the cathode and the anode, and we are having a focusing cup in the area of cathode in order to focus this electron towards the target, and the electrons is moving from cathode towards the anode. Anode is the target material, and from there X-rays are produced. So let us see what is meant by line focus principles. So from previous slides we discussed that X-rays electrons are coming and hitting the target anode. So the area where the electron is hitting, that area is known as the focal spot. So the area struck by the electron is called the focal spot of X-ray emission, and it is heated instantly. So too much of heat the target is getting when each electron is coming and hitting. During X-ray production, a lot of heat is generated. If the target is too small, it will overheat and burn up. In order to get a small focal spot while maintaining an adequately large target, a line focus principle is used. From line focus principle, provide a wide focal spot without compromising the resolution. So the image, a good quality image can be acquired with a small focal spot. So we have to use a large target. Since we are using a small target, it will be heated up and it will be burned up. So we have to get a small focal spot. In spite of that, we have to use a large target. So we are angulating the target by line focus principle, and that angulating principle is known as line focus principle. Here you can see the figure. The width of a target struck by the electron is AB, but when seen from the usual beam, its apparent width is CB. Okay, given by CB equal to AB sin theta. The smaller the angle, the smaller the size of the apparent focal spot. So CB is the area from the apparent focal spot. From there the X-rays are coming and the image resolution will be good, as well as we are angulating in order to reduce the heat burned up by the target. So what is meant by Heal effect? X-rays are produced at various depths in the target. They suffer varying amount of attenuation in the target. So when the X-rays are producing, there itself the attenuation is happening. There is greater attenuation for X-rays coming from greater depth than those from near the surface of the target. The intensity of the X-ray beam decreases from cathode to the anode direction of the beam. This variation across the X-ray beam is called the Heal effect. The effect is highly seen in diagnostic tubes because of low X-ray energy and steep target angle. The problem can be minimized by using a compensating filter to provide differential across the beam in order to compensate for the Heal effect and improve the uniformity of the beam. So what is meant by attenuation? Attenuation is the reduction of the intensity of the X-ray beam. So the X-rays are produced at varying depth. So the X-rays are produced in the target. So from the anode side, but from there itself it is undergoing varying amount of attenuation. Greater attenuation for X-rays is coming from greater depth that close near to the surface of the target. So the intensity of the X-ray beam is decreases from cathode to the anode direction of the beam. In this figure you can see the Heal effect. Here you can see the anode angle of about 15 degree. It represents to the line focus principle. So the attenuation is next to that, you can see the self attenuation. The attenuation is happening inside the target itself. So the attenuation means reduction of the intensity of the X-ray beam. So the attenuation, when it is coming down, the loss of the X-ray intensity towards the anode side, and it is going up towards the cathode side. So the loss of X-ray intensity at the anode side is known as the heel effect. Production of X-rays. X-rays are produced when rapidly moving electrons that has been accelerated through a potential difference of order 1 kV to 1 MV strikes a target, metal target. So the metal target is tungsten. So from this figure you can see the filament. Filament is the cathode and it is a glass, evacuated glass tube, and here you can see the anode as the target. The filament will be always cathode and the target will be always anode, and both the material is formed of tungsten. The kV range is usually seen in the diagnostic radiology, and MV range of beam is seen in the radiotherapy department. Production of X-rays. X-rays from a hot element are accelerated onto a target anode. The source of electron is the cathode or negative electrode. The electrodes are stopped or decelerated by the anode or positive electrode. The electrons move between the cathode and the anode because there is a potential difference in charge between the electrodes. When the electrodes are suddenly decelerated on impact, some of the kinetic energy is converted into electromagnetic energy as X-rays. Less than 1% of the energy supplied in is converted into X radiation during this process, and the rest is converted into the internal energy of the target. It means when the electrons are hitting the target, only 1% of X-rays is produced, 99% is formed of heat. So here you can see heated filament emits electron by thermionic emission. So by means of thermionic emission, the filament is getting heated up and the electrons are ejected, and it is moving towards the cathode, and the X-rays are produced when high speed electrons hit the metal target, and this target is embedded on a copper rod for heat dissipation. Electrons are accelerated by a high voltage. Again, let us see the physics of X-ray production. BREMSTRAHLUNG X-rays as well as characteristic X-rays are produced in the X-ray tube. BREMSTRAHLUNG X-rays is otherwise known as breaking X-rays. So here you can see two figures. So just keep in mind these two figures. In one figure you can see a center nucleus and a fast electron is coming, attracted towards the nucleus. Then it is changing the direction and going to some distance. So when it is changing the direction, it is losing its energy, and this energy is released as X-rays. In the second figure, you can see the high energy electron is interacting with the K shell. Means this is the nucleus, the nearby shell is the K shell. When it is interacting with this electron, it is knocking out this electron. So X-rays have a potential for ionization. So it is knocking out this electron, and a vacancy will be filled here, and the electron from the next shell will be filling this vacancy with the release of the energy, or it may be the release of X-ray energy, and this process is known as characteristics X-ray. So kindly keep these two figures in mind. Let us move ahead to see more about this. Bremsstrahlung X-rays. When an incoming free electron gets close to the nucleus of the target atom. So tungsten is a target atom. It is having a nucleus as well as the K element shell. So when this electron from the filament is coming towards the anode, that means the target atom, the strong electric field of the nucleus will attract this electron, thus changing the direction and the speed of the electron. So once it gets attracted, but it will be changing its direction. When the electron is changing its direction, the electron will be losing energy, which will be emitted as an X-ray photon. The energy of this photon will depend upon the degree of interaction between nucleus and electron, that is passing distance. X-ray originating from this process are called Bremsstrahlung, German word naming breaking radiation. So the other name for Bremsstrahlung radiation is breaking radiation. The X-ray energy depends upon the interaction distance between the electron and the nucleus. It decreases as the distance increases. Since the electron may have one or more Bremsstrahlung interactions in the material, and an interaction may result in partial or complete loss of electron energy, the resulting Bremsstrahlung photon may have any energy up to the initial energy of the electron. Also, the direction of the emission of Bremsstrahlung photon will depend on the energy of the incident electron. As electron energy below about 100 keV, the X-rays are emitted more or less equally in all directions. As the kinetic energy of the electron increases, the direction of the X-ray emission increases forward. Therefore, transmission type targets are used in mega voltage X-ray tube accelerator. These mega voltage X-ray tubes are seen in the radiotherapy department in linear accelerator, in which the electron bombards the target on one side and the X-ray beam is obtained on the other side. In the low voltage X-ray tube, it is technically advantageous to obtain the X-ray beam on the same side of the target, that is at 90 degree with respect to the electron beam direction. So this is what about Bremsstrahlung radiation. Again, let's see about characteristics X-rays. When the energy of the electron incident on the target, so it is also incident on the target, exceeds the binding energy of the electron of the target atom, it is energetically possible for the collision interaction to eject the electron and ionize the atom. So the electron coming from the filament should be having that much energy to overcome the binding energy of the electron of the target material, and it will be interacting with the K shell electron, and it will be kicking out that electron from that K shell, and the K shell will be having two electrons. So ejected K shell electron you can see in the figure. So there is a vacancy formed in the K shell. In order to fill this vacancy, an outer shell orbit will be filling. Outer shell is the L shell, and an L shell electron will be filling this vacancy with the ejection of a radiation. That radiation is known as characteristics X-ray. So the unfilled shell is energetically unstable, and an outer shell electron with less binding energy will fill the vacancy. Binding energy means the binding energy of the K shell will be high compared with the other shell, since it is close to the nucleus. As as this electron transits to the lower energy state, the excess energy can be released as a characteristic X-ray photon with an energy equal to the difference between the binding energy of the electron shell. With higher atomic number target and the transition involving inner shells such as K, L, M and N. Again we will discuss about continuous X-ray spectra. The Bremsstrahlung X-ray energies is ranging from 0 to the peak and back to 0, and this is referred to as a continuous X-ray spectra. The majority of the useful X-rays are in the continuous spectrum. The maximum energy will be equal to the kVp of the operation, and this is why it is called kVp. kVp means kilovolt peak. So in this diagram you can see a continuous spectra since it is increasing, reaching a peak, then coming back to 0. So which all are the factors which are affecting the X-ray emission? The output of an X-ray tube is described in 3 terms: quality, quantity as well as exposure. Quality means describe the penetratability of the X-ray beam. As we have studied, X-rays are having short wavelength, so it have long penetrating power, and that's the main quality of the X-ray beam we are using in diagnostics as well as for therapeutic purpose, since X-ray is penetrating deep to the body tissue. With higher energy X-ray photons having a larger HVL. HVL means half value layer and higher quality. Quantity refers to the number of photons comprising the beam. So quantity means number of photons. Quality means the penetrating of the X-ray beam. And the exposure. Exposure is a unit of radiation. It is a measure of ionization per unit mass of air. So another factor which is affecting the X-ray beam quality and quantity. So it is clear, you can see an increase in current. So current is MAS. MAS means milliampere second tube current, where S is the exposure time. So current, when we are increasing the current and increase in the quantity. Quantity means number of photons, but no change in quality. Quality means no change in the penetration of the X-ray beam. So increase in the current will increases the quantity. Quantity means the number of photons, but the penetrating power there is no change. While we are increasing the kVp, kVp is the voltage, kilovolt peak, an increase in the quantity as well as in the quality. So quantity of photon is also increased, the penetrating of the photon is also increased. Then added filtration. In order to filter the beam, we are using filters. More about filters we will be discussing in the upcoming topics. So we will be using filters. So when we are increasing the filter, added filter means a decrease in the quantity and increase in the quality. So it will decrease the quantity of the photons. So we are mainly using filters in order to shape the X-ray beam by absorbing the low energy photons, so that the skin dose can be reduced. For that we are using filters. So the quantity, it will be absorbing the low energy photon. So the quantity of the X-ray photon will be decreased but increase in the quality. Quality means the penetrating power. Then while increasing the atomic number, the target atomic number, increase in the quantity as well as quality. Then voltage ripple. It also the voltage ripple we are using, then it will be increase in the voltage ripple will result in decrease in quantity as well as quality. Number of photons will also be decreased The penetrating power will also be decreased. So with that, coming to the session of today's, thank you for your patience listening. Hope you all have enjoyed the session. If you have enjoyed, please don't forget to like as well as to subscribe my channel. Stay tuned for the next topic. Once again, thank you so much.